Next, let's go to page 396, where we have the definition of differentiability. A function is differentiable if it satisfies, if it has a neighborhood, okay, at a certain point that satisfies certain conditions. That has to do with the, actually this is defined from the linear approximation. That is, if the area divided by the distance go to 0. That is, if the slope of the area is going down like this, okay? So then if that is the case, the function is called differentiable. What that means in practice is that the function is smooth all over. There's no folds. The surface, that is. The function surface has no folds, okay? The folds are, well, pretty much not good enough, right? And so if it has no folds, then the differentiation equation will make sense. So, and that would be the definition. We're not going to look at the definition too much right now. We'll do so in the next section. However, we can still do this though. Let's look at example 4.24, where we demonstrate the differentiability. Now, please do this example as part of your homework. What you do is that you take a function and you want to show that it's differentiable at a certain point. In example 4.24, we are going to calculate everything according to the formula on the previous page. See, we'll just plug everything in here, okay? And then we're going to check to see if the limit of the error divided by the distance to the error, divided by the, not the distance to the error, sorry. The distance from the point to the point in question, okay, is 0. Now, to do that, every part looks pretty good, right? Except that, so you calculate everything, find out what the partial derivatives are, what the function is, and so on. And then eventually, you're going to be calculating this. You have to calculate this thing equal to, and prove that this thing's going to 0. Now, that is not that easy, okay? However, your book showed a very neat trick of how to do that. So then we have, first we have, for example, look at this very carefully, okay? And check out this neat trick. Now, everything looks okay at first. And we have the limit is here, okay? And then we have everything goes. Now, I decided to write it down to explain it better. Now, we got to this point, okay? Everything is resolved and we got here. Now, notice at this point, something interesting happens. This thing is a square, and the square root, of course, is also positive. So this whole thing is bigger than equal to 0. Okay, we'll draw it right here. This limit will be bigger than or equal to 0. So being that that's the case, what we're going to do, it is positive, we'll add something to it so that the top and bottom matches. We're going to, in the next step, we're going to add y plus 3 squared. Otherwise, everything else stays the same. We're just sticking y plus 3 in there for some reason. And you think, why is that? Well, the reason was, you notice we stick it right inside the parentheses with the 2 factored out front, okay? And that's still, this becomes an inequality instead of equality, and that still works, right? I mean, we're just saying that it's less than this, okay? If you add something, of course it's less than. So that's good, and that is going to go to, then you can cancel this out. Once you cancel this out, then you have the answer here. Then you have just, what you are left is the square root of that stuff, as your book shows, see? So that's the last answer. And at this point, we'll let x go to 2 and y equal to negative 3, and therefore, this whole thing goes to 0, okay? So this equal to 0. Now, if it goes to 0, if it goes to 0, and it's bigger than or equal to 0 to start with, that means the limit is, that means the original limit before we add it has to be equal to 0. It's the squeeze principle, right? And so that is the neat trick that your book used to prove that the error goes to 0. Not just the error, but the error divided by this. this square root thing, okay, that as we required for proving differentiability. Now, this trick only works because we happen to have this thing to be a perfect square. What if it wasn't? Or what if it's negative? Couldn't it be negative? Sure. If that happens, you're out of luck. But right now, we're in luck. We don't have to worry about that. So and that's how we managed to prove example 4.24. So please finish this homework example as part of your homework. And next, we'll go to the next page. And next, let's look at page 398, where we have, we're going to look at that same function again. That thing that has a weird fold at the origin, okay? And then we're going to plug it into the differentiable, whatever that is, that formula that we saw earlier, and to calculate the e, and then see if we can prove that it is at the origin that it is not differentiable. Because anytime you have a fold, it's not differentiable. But can we actually prove that? Now, so let's calculate that. We'll follow the formula. Okay, which the formula says you have f of xy equals to f as 0, and then fx times x minus something, and fy y minus something, plus e of y. Now at this point, remember, x is evaluated as 0, and y is evaluated as 0, and the function of value f as 0 equals to 0. So everything is 0. Except for the exy at the end. So then exy equal to the function itself, being that the function is that. So we got that far. And then we plug it into the formula as we required, which is the exy need to be subtracted by the distance. I mean, yeah, divided, sorry, did I say subtract? I mean divided by the distance according to the formula. And we have to figure out what this limit is. If it's 0, that means our function is differentiable. If it's not 0, then it's not. So once we do the division, see the 3-level division, and then we end up with this thing. And how are we going to calculate the limit of this? Well, the limit of this is, let me write it down. Now, this limit doesn't exist because we can do this. Like, first we let y equal to x, okay? Then the limit will approach, it will become x squared divided by this stuff, right? So then the limit will be positive, right? If y equal to x, as they both go to 0. But if we let y equal to negative x, then this limit will be negative, right? Because it will be x squared up here with a negative sign. So the limit is different depending on how x, y approach 0. And then the limit should apply for, doesn't matter how they approach, okay? It should be the same. So being that the limit is different, then we know that this limit does not exist. And that's why this function is not differentiable at the origin. Actually, I think I'll write it down exactly what it is. Okay, let's just write it down. If y equal to x, this will be equal to x squared, okay, divided by, the bottom will be y equal to x, so it's 2x squared, which equals to 1/2. Whereas if y is minus x, everything is the same, except there's an extra negative sign here, so it becomes minus 1/2. So the limit is 1/2 approaching one direction and minus 1/2 approaching another direction. And therefore the limit doesn't exist at the point of 0. Continuing at the bottom of page 398, we have the theorem 4.6. Differentiability implies continuity. That is true in 1D and definitely true in 2D. Okay, if it's differentiable, it better be continuous. And we're not going to prove that, but we're just going to look at the next page. And then, of course, the opposite is not true. Continuity under no other condition implies differentiability, because differentiability is a more stringent requirement, as that example we've been staring at shows. That function we've been looking at this whole time is this one is continuous but not differentiable at the origin. So next, let's look at, what is this? Here's a next theorem of differentiability. Now, instead of proving that E business, which is most of the time extremely difficult to do, okay, we have found a side trick, okay, a better way of proving differentiability. That's much, much better. And that's theorem 4.7, which says that if you let Z is f of y, okay, and if in some domain, if the condition that in some neighborhood of some point that we're interested in, if three conditions exist, okay, that is all f of the function, the partial with respect to x and the partial with respect to y, all three things exist in the neighborhood of this point and are continuous at the point itself. It can be continuous elsewhere too, but at least it's continuous. All three functions are continuous at the point itself and exist in a small neighborhood around that point. Then f of xy is differentiable there. That's much easier to do than try to calculate some random error, which is, as you can see, even this problem we were only able to do it because of unusual amount of luck, okay, that we were lucky that this happens to be a positive all the time. So anyway, so here we got a much easier way of proving differentiability. And having said that, we are not going to prove this theorem, but also show some situations that if a function isn't differentiable, then it stands to reason that one of those three, at least one of those three conditions can be true. The condition that either f, fx, or fy are all continuous at this point. One of them has to be not continuous if the function is not differentiable. Now to show that, we will look at that same old function again, okay? And then we will take the partial f. Here's a function which is continuous at 0, okay? And then we'll look at partial f, partial x, and partial f, partial y, and figure out are those things continuous at 0 at the origin. And to do that, we will, let's see, do some calculations. That is, well, first you got to take the partial derivatives, which did come out, and we'll just assume that that works out okay. All right, yeah, you're going to have to do the quotient rule or whatever. But let's say it comes out nicely, and then we'll look at one of these things and figure out what is the limit as x, y approaches 0. Now to calculate that, we'll use a standard trick similar to what we're doing right now. Is instead we let x equal to ky. K can be 1 or any other thing, really, we don't care, okay? So instead of equal to, we'll just say k is some constant. You plug it in, and then see here, then we will I'll move over here. Okay, and then we'll do some algebra to clean stuff up a little bit. And we notice that when you're done with the algebra, you are able to pull y out, okay? So you have a bunch of k's that's squared, and you take the square root of, so all that fraction is positive, okay? And then inside the limit, and you're letting y go to 0. And you end up calculating because you took the square root, and you plucked y out of a square root, so you have to slap on the absolute value to make sense. But the other y doesn't have an absolute value. So you're in an interesting situation where if y is positive, that fraction will be 1, whereas y is negative, that limit goes to -1. So the limit goes to two places, which is that the absolute value situation, okay? If the limit goes to two places, then the limit does not exist, and therefore this the condition that the partials are continuous is not satisfied. That's how we know that it doesn't this theorem doesn't apply for those functions, because their partials are not continuous as required. So next, let's look at differentials. Next, let's look at page 400, where we're going to talk about differentials. Now, what is a differential? What happens is the differential is similar to the differential in Calculus 1, except that this time we're going to call dx delta x and dy is delta y, and define dz as the partial derivatives of the value at the point that we're considering, okay? And dz will be fx dx and fy dy, evaluated at our specific point. Now, remember that delta z, okay, is just the actual difference between the function moved by delta and subtracted by original value. So then as a result, what we're going to do is using delta c to approximate dc, which is that formula that we just looked at. And so when you beat that formula around a little bit, you end up having this. That is the f of x plus delta x, y plus delta y is being approximated by fxy plus the partial times delta x and the partial times delta y. And well, that seems like a lot of symbols, but there really isn't much to it, okay? We're just doing, well, you do have to do some partial derivatives. After that, you're just doing addition, or I mean multiplication and addition. That's about it. And to see what I mean, please do example 4.25, where you plug in different things and seeing what dz is and what delta z is, and see what the difference is. dz is the approximation, whereas delta z is the actual number. And you might wonder, why are we approximating this thing again? It's for in case where you don't actually know what the function is, but you actually can calculate what the partial derivatives are. That does happen. And as a result, then you can use these partial derivatives to predict what the value is, because you don't actually know what the function is. So anyway, and that's done in applied mathematics. But in the meantime, let's do this simple little thing. Well, when I say simple, I just mean that you don't have to do a lot of complicated work, but it's still tedious, of course. You gotta type all those, do all those numbers. And yeah, so please do that as part of your homework. And with that, let's talk about the last item in this section, differentiability of functions in 3 variables in the next page. Well, the 3 variables changes nothing, okay? So the function is in 3 variables, and what you're gonna do to prove differentiability, we're gonna define exactly the same as 2 functions. That is, you will have the function is differentiable if this relationship of at the point of the value of the function at the point plus partial x, okay, plus partial y times x minus x0, partial y times y minus y0. Then you got one more thing, partial z times what, z minus z0. And then you plus the error, and guess what the error is? It looks identical to the other error, and the error is now identical, except you have a 3rd variable and a 3rd thing to stuck on the bottom. Okay, you have the Pythagoras theorem in 3 variables. So all x, y, z go to the point as you do the division, and if this limit goes to 0, then your function is differentiable. Right. Anyway, now this function, as you can think, is not a 3D object. This function is a 4D object. So what does it mean that it's differentiable? We cannot visualize this function because this function has to exist in 4D, but the principle is the same, okay? We simply assume that this thing's smooth in 4D, which we can't see, but we can still work on, using the same principle from 3D. If it works for 3D, it works for 4D or any other Ds. So that marks the end of this section. For homework on page 403, please do problems 167, 173, 177, 181, 83, 91, 99, and 207. Yeah, and I won't be talking about them because they're all just basically tedious work. So we will but it's still good for you to do this kind of stuff because we are working stuff in 2 or 3 or more dimensions. So it's good to do to work on. The tedious work is good for giving you a feel of what you're doing, okay? And it will prepare us for the next section.